Okay, let's continue after a short break. So areas of application of spectral transform include many tasks and could be used in absolutely different, quite different, even opposite fields of engineering, technique, mathematics, and other sciences. What would be interested here among this list for our today's topic is a data compression. So you understand that the task of data compression could be very useful, especially taking into account that a lot of data are now in the modern world should be proceed, analyzed, transferred, received, and so on. So the question of the compression of all these massives of data is very actual. And a very useful instrument for this could be wavelet transform. And if we will try to continue the analogy with a bridge, like in Fourier and other spectral transform, where we had only one bridge, that was connected original function and the spectrum. So the question is, how could we construct more than one bridges and to analyze more detailed property of the original signal, not only just original and spectrum and back. So would it be possible to find some another algorithm that will bring us somewhere in far away and to see like different features and different characteristics of the signal from a different point. So in order to see to the signal from the first bridge, second bridge, and so on. That is the question, and the answer to this question is actually wavelet transform. And so existing spectral transform, I already told a little bit about it. It's including different transform and different types of the how to deal with original function. It could be Fourier, classical one, also Laplace transform that is very popular in electrotechnic and electronics. Also that transform that allows to deal and to analyze the signal of the discrete time, like discrete systems, to analyze the processes in this system, and so on. But as regards to the lower part here in the list, we have wavelet transform that allows simultaneous analysis in time and frequency domain in the same time, that is not allowed by any other spectral transform. Neither Fourier nor any other spectral transform, only in wavelet, and that is most interesting. And actually now we are coming to the next point in our list. It's the principle of wavelet. I would say that just very short historical info, that this concept was proposed by two famous French scientists, French mathematicians, Yves Meyer and Jean Morlier. First one, Yves, was awarded by the so-called Abel Prize, and unlike Nobel, this is like an analogy of Nobel Prize, but for the mathematician. And Jean Morlier was like a creator of one of the most famous wavelet functions that is called by his name, Morlier wavelet. And the concept of wavelet transform was actually introduced in the 70th year, but it was not actively used in different fields like it is used now until the late 80s and early 90s years. And only after creation of the fast-acting computers and fast calculating algorithm. It became possible to use this method in order to apply it for very large massives of data, and actually for non-stationary signal, like for example here. So it was always a problem how to deal with the signals like these non-stationary signals. When we are going back to Fourier transform, so we know that Fourier transform is operating with the infinitely wide trigonometrical basis, cosine and sine function, and it is very well suited for the stationary signals. But for non-stationary signals, it is difficult to apply Fourier. Nevertheless, it is applied, and a different modification of Fourier, like fast Fourier transform and others, are successfully used. But by its nature of cosine and sine trigonometrical basis, it is most suitable actually for the stationary signals. When we are talking about non-stationary signals, for example, the signals that we are dealing with or were dealing with, it was like a signal of power consumption of microgrid. So we analyzed the characteristics, the signal of power consumption during some period, for example 24 hours or 1 month or so on. So our task was to predict these values, to predict energy consumption, and to correct the algorithm of the energy control. Now we are dealing with the signals of traffic data, and it is also non-stationary signals. So you could imagine that it could be a lot of different non-stationary signals that are to be analyzed. And okay, and now application of these new type of a method of wavelet actually, and you can see here the different possible, but not, of course, it's again, this list is not full, but possible areas of application. You can see that somehow they are overlaid with the application of Fourier transform and other spectral methods that I showed you before. So it also could be used to solve the differential equation, actually to analyze transient and steady processes, to make an image recognition, and more broadly the pattern recognition. And also it is very suitable for non-stationary signal, as I said already, and for the images. We also use it for image. And the main outcome that we obtain from this is a data compression and a simplification. So images of various types could be analyzed. For example, it could be medical images, X-ray, iris images, satellite images of clouds, and so on. And again, convolution and mapping of large volumes of data. Talking about how similar or how different it from the Fourier transform, here a couple phrases about the comparison. So regarding the Fourier transform, we have values of the signal and we have weight coefficients. And we know that the basic function of a Fourier transform, like a exponential function or cosine or sine function, are imaginary, so they have an imaginary character, and argument is harmonic, and it depends on frequency. Unlike it is in wavelet. While in wavelet we also have weight coefficients that are wavelet functions that are also like a coefficients in Fourier. But a very interesting thing is that all wavelet functions are obtained from the same function that is called parent wavelet. And the main difference between Fourier and wavelet transform is that wavelets are localized in both time and frequency domain. And the standard Fourier transform is only localized in frequency. So this gives us the possibility to analyze a signal and the features of a signal at the same time in a frequency and in time domain. That is very interesting and attractive for the researchers, of course. So I already mentioned parent wavelet. This is a function that is the basic function from which all other wavelet functions are obtained. So it's one of the main things in wavelet transform, the parent wavelet. By the way, the word wavelet means like a small wave, like one way. While the suffix let means like something small, like a piglet, for example. Yeah, so wavelet, like a very, very small wave, like you see on this beautiful beach. So it's well located, soliton-like. Do you know what does it mean, soliton? Okay, it's like a one, yeah, one wave. Okay, thank you. And not every small wave could be a parent wavelet. There are like a set of demands that are to be fulfilled in order to make this function able to be a parent wavelet. So these demands are listed here. At first, it should be an oscillating function, so it could not be a constant value. It should change its sign from minus to plus at least one time. Maybe more, but it should oscillating. This is the first demand. The second one is the absence of the component of direct current. It means that it should have the same square in the positive direction and also in negative direction. Like, for example, sine function. So we have a positive half period and a negative half period, and square here and here are the same. Also, it should be here. Second is a rapidly decreasing over time. So it should be really small wavelet. So it should oscillate and very soon decreasing to zero. And also, of course, it is very important not to be able to make a direct transform, but also to come back to make an inverse transform. So inverse function should be existing and it should be definitive. This parent wavelet is, we will mark it, we will note it using notation psi, a Greek letter psi, from t, because it's dependent on time. And the wavelet zoo, so the possible candidates to be a parent wavelet, there are these possible waveforms that could be, and actually that are used as a wavelet basis, as a parent wavelet, is a wavelet zoo that were proposed. It's a classical, it's not something new. So we have a Dobeshi, very well known wavelet that is already embedded in a most calculation program like MATCAD, MATLAB, and so on. The Mexican hat, and also you can see this funny image of Mexican cat. You can compare it with the waveform and also other. And also you can see that the most simple from this, even just observing, we can see that the most simple is a wavelet that is called Haar wavelet. Oh, sorry. Here. Haar wavelet is just rectangular wavelet that has an oscillating. Actually, all these functions have an oscillations. You see, they are changing their sign from plus to minus and vice versa. But the Haar wavelet is most simple. Why? Because it takes only two values, -1 and +1. So it's very difficult to create something more simple than +1 and -1, right? Okay. But I will show this Haar wavelet you later. in my presentation. And regarding the wavelet, there are two basic operations that are executed in each step, because wavelet, do you remember the picture with the bridges? Wavelet is like an iteration method, iteration processes. There are couple steps, couple levels. How many levels? It depends on the original function. The more values of original function we have, the more levels of wavelet we will be able to do. And in each level, two basic operations are applied. It's scaling and shifting. So when we take one of these wavelets from the two, wavelet of heart, Mexican heart, Lubezki, what else, then we will start to scale it on a horizontal axis and also on a vertical axis. This is first operation, and then after this we are starting to move it along the axis, horizontal axis, so shifting. So scaling and shifting. There are two basic operations in a wavelet that are executed at each level. I will show you also again in my presentation. And the question is how to cover the entire axis from minus infinity to plus infinity using only this small wave, only this small function. And the answer is directly scaling and shifting to cover all the axes. Here is an answer: set of shift and transfer along the axis. And most simple, just to take integer values of shifting, just to use like a discrete time slot to shift the small wavelet each time to one slot. And here is the solution. And from basic parent wavelet we are obtaining associating function or daughter function. And how to obtain it from only one function? The answer lies on this formula. So we are using here parent wavelet that is noted and indicated by the Greek letter psi, and also you can mark that there are two parameters, a and tau, that are using to obtain from only one function the set of other functions by scaling and by shifting. So we have here the parameter a, that is variable scaling coefficient, and it is responsible for the scaling on vertical axis as well as on horizontal axis. And we have tau, that is shift factor. It is responsible for the shifting. And so regularities are here. The same formula with these two parameters. You can see that parameter a is here in two places. Here before the function of parent wavelet, it is responsible for the scaling on the vertical axis, and also in the brackets in argument. And here it is responsible for the scaling in horizontal direction. And the parameter tau appears only one time. It is responsible only for the shift. So regularities are here. The more a we will take, the less amplitude, because it is in denominator, and the less argument, because it is also in denominator in argument, we will obtain. It means that we will obtain less frequency. What does it mean? Like less frequency. So, for example, sinus alpha and sinus alpha divided by 2. In the second case, the frequency is 2 times less. It means that the function becomes wider by horizontal. And as regards shift, the positive values of tau mean shift of the function along horizontal axis. Negative values also along the horizontal axis, but to the negative direction. So by changing these two parameters, A of tau, it is possible to create the whole set of the functions that will be different, that will differ from each other, with the more or less frequencies, with the more or less amplitude, and located in different time slot. And this set of the function could be very effectively used for the analysis of non-stationary signals. And it is also important to distinguish a continuous method and a discrete method. Like always, like in Fourier transform, so we have continuous Fourier transform and discrete Fourier transform. The same with wavelet. There are continuous wavelets and also discrete wavelets. And in order to go to the discrete wavelets that are more preferable, taking into consideration that we are living in a digital world and we are using digital techniques and digital methods also for signal processing. So it would be favorable to obtain the discrete wavelet, and they are obtained from the continuous by discretizing all to these parameters, scaling coefficients and the shift and also the time. And now we are going directly to the next topic. It's a Mallet algorithm that is actually the core of wavelet transform. And we can see here the main idea of wavelet. The main idea is also called multi-scale analysis. So we are able, using this tool, to consider the original function on different scales, multi-scale. So we can go more deep and study and investigate the very, very small property of the signal. And also we can go upper and see on the large scale about the regularities of the signal. So signal is divided to some frequency bands, and we are applying so-called low frequency filter and high frequency filter. And each signals are at each level, the signal is split into two components. In classical wavelet theory, there are two components at each step. First one is the trend, like a low frequency component that reflects the most essential changes of the original signal's trend. And the second one are utilization, like a high frequency component around this trend. How to use it in signal processor? We can investigate separately trend and utilization or high frequency component. And for example, if you take high frequency component like noises and investigate it, somehow we possibly could be able to understand what are, for example, the sources, the reason of this appearance of these noises. And of course, we should be able not only to take a direct, to make a direct transform, but also to come back, to make an inverse transform. When we are doing direct transform, we are going from original function to different levels of wavelet transform, and on this way we are calculating a set of different coefficients. At each step, like at each bridge, we obtain a trend and a noise. Then again, we take only this trend and go on further and obtain a trend, another trend, and a noise. Then again, take only trend and obtain new trend and a noise. Each new trend will be more smoother than the previous one. In such a way, we will be able to smooth the original function more and more at each next step. At each level of decomposition, so this process is called decomposition, when we are decomposing original signal into the components, trend and noise, and so on. This process is called decomposition, and we are obtaining decomposition coefficients. There are two groups of these coefficients, one for trend and one for noise. I will show you later. And all this process is called algorithm of Malla. Why Malla? Because this is after the name of, again, a French mathematician. So French guys were very and are very active in a theory of wavelet analysis. Stefan Malla. And this algorithm that is the core idea of wavelet transform is called after the name of Stefan Malla, Malla algorithm. So we have original function here, and we are going step by step. At the first level, we are doing decomposition when we are going from the left to the right. At the first level, we have only coefficients that are noted as S coefficients, and they are existing on this first level, only this coefficient. After this, we are at each next level, we are able and we are calculating two groups of the coefficients. One is approximating coefficients that are noted as S, and they are forming trend, so S coefficient, but it's not only one, it's a group of coefficients. And also detalization coefficients that are noted as D, and they are used to form a noise around the trend at this level of decomposition. And after this level, we have this block with the arrow and 2. It means that the number of values are decreasing 2 times every time, at every step. So if we have, for example, let's say 8 values in the beginning, so after one step we will obtain 4, then 2, and then at least 1. So at the end, we are obtaining only one S and one D coefficients. Unlike at every previous level, where we are obtaining not only one, but one group of S coefficients and one group of D coefficients. So in such a way, we are able to do all these levels of decomposition, and after every level, their number will be decreased by 2, decreased by 2, decreased by 2, and so on. So actually, maybe it's a little bit difficult to understand when just looking to the slide, but when you are starting to work with it and just to apply it for the concrete signal, it becomes far more simple. And talking about simple, let's go to the most simple wavelet that even could be. It's Haar wavelet. And this is like a parent wavelet. You remember oscillating function that could be and is allowed to be a parent wavelet is this function that you can see on the right side of the slide is a parent Haar wavelet. So it is defined on the unitary interval, and in the first half of this interval it takes a value of +1 and the second half -1. And also, in order to realize a scaling, you remember one of the basic operations of wavelet is scaling. In order to realize this, in every wavelet, not only Haar, in every wavelet, we are always using this scaling function, phi. It is noted by the Greek letter phi. So psi is a parent wavelet, phi is scaling function. Also in analytical form, it could be written down like here for phi and here for parent wavelet psi. And remember that we are using scaling and shifting at each level, so both these operations are applied at each step. So we are applying scaling and shifted for scaling function, and here is a formula for this that reflects these two operations, scaling and shifting, and also for the parent wavelet. These two formulas are very, very similar. Actually, they are analogical. The only difference is these Greek letters, phi in the first and psi in the second. And we have two more notation, two more letters, J and K. So the J is the level of decomposition. So Wavelet is a multi-step algorithm, also level of decomposition is like a counter. But this counter is changing from maximum value to 0. Maximum value is, as you can see, J max. So J is changing from J max, then J max minus 1, and so on till 0. And this maximum value, J max, is defined from directly original signal. So it's a question, what signal do we want to analyze and how many values these signals have? Because we are talking about discrete method, so it is just an demand for the number of values in original signals. It should be the power of 2. If not, you have to do something in order to make it the power equal to power of 2. So you should just eliminate, for example, couple values and analyze them later, or maybe to split the original signal into the parts for such a way that each part consists of 2 in something power value. So if you are already did this, you can see that we will obtain n capital equal to 2 in the power n. So it is a number of values that is a power of 2. Okay, and depending of this power, we will be able to say how many levels of wavelet we are theoretically able to fulfill. For example, if we have 8 values in the beginning, you remember that after each level the number of values decreases in 2 times. So at first level the number doesn't change, so we have 8. After 2 levels we have 4, after 3 levels we have 2, and after 4 levels we have only 1 value. This is 0th level. So if we will have not 8 but 16, for example, values, so we will have more values. If we have 2 in the power 10, 124 values, so of course, obviously we will have possibility to go through more amount of levels. And at the maximum level for Wavelet, but not only, for all others, we have only S coefficients. Do you remember? I would like to show you again this scheme of Mallet algorithm. So here at the maximum level, J max, we have only S coefficients, and in case of higher wavelet, they are calculated through the values of original signals using this formula. So in this formula we have values of original function y, and we are calculating these S coefficients of maximum level. For every other levels except maximum, we will obtain not only S but also D coefficient, but at maximum level only S. For every other level, we will use this S coefficient from maximum level in order to calculate both S and D coefficients using this recurrent formula. In the right part of these two formulas, we see S, J. So it means the S coefficients from the previous level J. And using this, we are able to calculate S and D coefficients of the lower level, J minus 1. So this is like a kind of recurrent formula. And here Sj is like a vector column that contains the values of S coefficients from the previous level. And again, our bridges. In order to go not only in direct transform, but also to be able to return back, it's called reconstruction of original function. So if we went couple steps, couple levels, and stand somewhere, anyway, we are able to come back to reconstruct the original function. So we can do it after one step, one level, and return back. We can go further, 2 levels, and can go back up to the end, and also we are able to come back and reconstruct original function. So inverse transform in case of wavelet is a reconstruction of original function. It is possible at each level. For example, if we are stopping at level J max, so not going further, just stopping here, we can do it by using this formula that contains coefficients S of this level J max. And using these coefficients, we will multiply each of these coefficients that were calculated on a maximum level by a certain scaled and shifted scaling function, because phi that is present here in formula, this is a scaling function. If we are not stopping at maximum level and went further, after first step of wavelet decomposition, we already obtain not only S but also D coefficients. And again, we can come back, return back, and reconstruct original function. To do here, we have to use this formula. And in this formula, as you can see, we use not only S but also D coefficient, because after this first step of wavelet transform, we already have S and D, and we should collect them together in order to reconstruct the function. And at least if we went up to the end and obtained all kinds of coefficients, all possible coefficients that are theoretically achievable, so we have a lot of S coefficients and a lot of D coefficients, we also can come back, return back, and reconstruct the function. In order to do this, we are using more long formula, of course, because we have to collect all these values. But the main idea is wherever we are stopped, in order to come back and reconstruct the original function, we have to collect, to take S coefficients of this current level when we were stopped, and D coefficients of all previous level. So S coefficients that are responsible for the trend only for this concrete level, not any other S coefficients, only for this level, but plus D coefficients of all other levels. And you can see it here. So we have S0, 0, S0, 0. For the coefficients S, it's only one coefficient of the last level. D0, 0, it's a coefficient there of the last level, and also all other component of this formula contains only D, D, D. So we are collecting all these detailing coefficients. So not going deeper in the formula, I will just want you to understand the logic about it. Okay, and here there is a proposed methodology that we are using, how we are using this mathematical apparatus, this approach in our work. Actually, we are doing it like a tool of pre-processing of time series. So in case if you or we have signals that should be for example, predicted, or transferred somewhere or compressed in order to take less memory. So we are using as a first step a wavelet transform in order to compress the data. Then we are feeding a neural network by this pre-processed data, and then we were able to do this to fulfill our task, prediction or compression or whatever, more effectively compared to the case when we didn't nothing with the pre-processing or just using pure neural network. So 3 main blocks is the network time series that we have in the beginning, then discrete hard wavelet transform, but it also could not be not necessarily hard, but wavelet transform like a pre-processing, and then neural network. And yeah, we have a lot of interesting results. Of course, it's not the subject of today's lesson, so I would be very grateful for your attention, for your presence, for that you come here. Thank you very much for the attention, and now I would like to see to the result of our interaction.